So let's begin. I want to thank everybody for coming, and I'm going to read the intro that I have for Ketzel. It's my great pleasure to introduce our speaker, Ketzel Levens, whom I first met in the fall of 2018 when she was a junior transfer from Carleton College and a refugee from physics. We get quite a number of them. Nearly immediately, she began recounting her experiences as a kayak outfitter in Bayfield, Wisconsin, home of the beautiful Apostle Islands National Seashore. Lives are lost each year in that park as convective storms can develop quickly and turn the waters very angry, very quickly. And despite this looming threat, there's no mesoscale forecast model or data collection network dedicated to providing forecasts and current weather information over those islands and treacherous waters. Ketzel wanted to change that, so she effectively got me and Professor Michael Morgan together, and then within a couple of days brought in Dr. Brett Hoover, and within a few weeks we had a Wisconsin idea proposal that made it to the final round of the competition in 2019. During the proposal development process, Ketzel had contacted the National Weather Service, several offices actually, the National Park Service, Bayfield's mayor, the local business interests. It was just incredible, the energy that she dedicated to this. You know, University of Wisconsin is the big leagues, so even with that energy and effort, the competition was fierce and we didn't win. But undeterred, Ketzel secured a competitive summer internship with Dr. Marty Ralph's group studying atmospheric rivers at University of California, San Diego. And the work that she'll present this morning combines aspects of that experience with her desire to know more about winter storms here in the upper Midwest. And I have to say, it's been a real pleasure working with Ketzel, and I hold out hope that she'll eventually return after graduation to pursue a graduate degree. Any scientist, and all of us at UW are in the first round of the draft, any scientist would be lucky to have her intellect, energy, persistence, and buoyant personality as a feature of their working environment. So without further ado, Ketzel Levens.
Wow, thank you very much for that. Hopefully everyone can hear me and see my screen for my presentation. I apologize because there is construction outside my apartment right now, so if a couple backup noises appear suddenly, it's not my fault. I am real bummed to not be in 1411 presenting this with you guys, but hopefully this doesn't diminish the quality at all. This research, as Professor Martin said, has followed me for the last year from San Diego to Madison and then finishing up in my childhood bedroom of all places, and I'm really glad that it's here today with you guys. So without further ado, I would like to introduce my senior thesis, which is Diagnosing the Moisture Source and Transport Pathway for Banded Snowfall in a February Atmospheric River Containing Midwest Extratropical Cyclone. So after that mouthful, let's get into it. So this was a system that came across our area and a lot of other regions last February in 2019 from the 22nd through the day on the 24th of February. It was a pretty, really kind of honestly beautifully stereotypical Colorado low system that tracked from the southwest all the way to the northeast and across into Canada. You can see the 72-hour snowfall in meters here on the right, and it laid down this really massive, heavy snow band across the Great Plains and Great Lakes. There was some freezing rain along that kind of southerly snow gradient, and then not pictured here is really heavy rain that fell for several days over the southeast to states like Mississippi, Alabama, and Tennessee, which had already been inundated by a lot of water that year. This just really accelerated the fact that they were very saturated at that point. So like I said, the snow fell all over the country. It started even in Las Vegas in the southwest, continued across the Great Plains. This is Iowa, and we all know how big a snowplow is. So this is pretty impressive. And then over the Great Lakes states, even in areas that didn't see a lot of snow, there were some really high winds that made for dangerous blizzard conditions, leading to traffic accidents and huge ice shoves at the end of Lake Erie. So it was a really impactful system as far as the winter weather was concerned. And then in the southeast, like I mentioned, I had a lot of rain, which led to landslides like this over roads and over some houses, and then just so much water that led to just roads being flooded and parking lots being flooded and everybody seeing a lot of water overall. So getting into some of the synoptics of this system, I'm going to go through a couple time steps to just discuss and make sure everybody has a good idea of what's going on a meteorological scale. This first image that we'll look at for these time steps is our kind of surface obs from GFS reanalysis. So we have mean sea level pressure in black, our temperature in green, and it's dashed where it goes below freezing, and then 6-hourly snowfall is in the shading, that kind of blue shading. So we can see at this initial time that this is really when the storm is just starting to get itself together in the southwest. It's not a very low central pressure yet. And then this next figure is going to be our 700 millibar Theta E isotopes. And this is used in order to kind of analyze some of the occluded structure and look at where our moisture and temperature gradients are throughout the storm. And what we're going to look for is that kind of traditional notch feature that I'll point out once we get to it. But we can see that it's really not here yet. At 300 millibars, what we're looking at is our 300 millibar heights in black, and then our jet feature, which is contoured in meters per second with the scale on the right, with the central low with that red L. What we can see here is that at 300 millibars, that low is sitting in a prime spot where it's having mass evacuated really strongly from curvature effects in this shortwave trough at 300 millibars. So overall, this low has a lot of places to go. If we step forward 6 hours, we can see that our low has progressed to the northeast. Our snow is becoming a little bit heavier, but that temperature environment is still a very kind of linear feature cutting throughout the storm, though we are starting to see that kind of notch in the Theta E gradients with a really strong gradient starting to build along the cold front. And we can see that kind of, let me see if I can get my laser pointer, curving cyclonically around the center of the storm. And at 300 millibars, we still have that shortwave trough that is helping the divergence aloft for this mass evacuation over the low, as well as a kind of increasing strength in the jet. And if we continue to step forward, this is the time when obviously we can see central Wisconsin is just getting hammered. And this would be the time that the max snowfall fell around Land O'Lakes, Wisconsin at 16 inches in 24 hours. And this low has progressed very deeply at this point. We can see it's now at 994, so it's starting to kind of rapidly deepen, and even in the surface temperatures, oh, I'm sorry, this is 2 meters temperature, I think I said that, we can see this kind of characteristic notch feature even here, and as we look at the Theta E gradients, really strong gradient along the cold front with that notch following back into the occluded quadrant. And at 300 millibars, we still have this shortwave trough feature that is helping this low progress and deepen, but we also see pretty significant strengthening in the jet at this point. And so this low is really being helped along by both curvature and speed agiostrophy at this point. And that's going to help it deepen even more into the beginning of the day on the 25th, when we can see that this storm deepens further impressively as it makes its way across the international border at 982. And this was kind of about the lowest the storm got as it made its way further to the northeast. Continuing with that occluded kind of style environment in the Theta E, but it's not the most strongly occluded cyclone that you'll ever see, and I will be the first one to admit that, but it did have really significant effects as far as the snowfall went. And then we can see here that that low is starting to sit in a not so ideal place as far as the heights are observed. It's really starting to locate itself at the base of that shortwave trough, but I think at this point it is still being aided along by some speed-induced effects in the jet exit region. So that gets us kind of this picture of this storm that's traveling along, has these really severe impacts on our area and a lot of the Great Plains as far as the snow is concerned. This is water vapor. Hopefully all of my videos and GIFs play for you guys. So these warm colors are the really dry air, and then the gray and the cooler colors is where you have really moist air in the water vapor satellite imagery. And so you look at this, and I guess I look at this, and I think, where is my snowfall coming from in the Great Lakes? You know, I was a little kid from the meteorologists on TV that we would get air from the tropics. It would help our snow form. So really, with my research, what I wanted to do is I wanted to analyze where this moisture was coming from, I identified an atmospheric river characteristic that would deliver moisture into the system. And then further from that, I wanted to understand how that moisture got involved within the cyclone, and then furthermore, how it was forced into snow. And I really wanted to tie it into, I'll come back to this image later in the presentation, but tying into these major cyclonic flows that we know about within these systems, and how an atmospheric river can interact with that, and that's what I did at Scripps, and then how further that moisture is transformed into snowfall in the occluded quadrant. And then this is just to give you guys an idea of that kind of 3D structure of how is this northwesterly quadrant of a mid-latitude cyclone attached to the tropics. And so what I did with my research is I said, okay, I'm going to identify an atmospheric river that acts as this feeder airstream, that's the FA on the left here, and how that interacts and flows into the storm. I identified what forcings are created to make that snowfall happen. And then the last piece of the puzzle was really tying it all together and saying, okay, how do these pathways go from these tropical exports all the way up into the banded snowfall? So we're going to take a look at that, and we're going to tie the entire picture together in this presentation. Briefly, I'm going to talk about what I did this past summer. This is research that I have already presented on in October. I know everybody didn't make it to that, but really for the sake of time and not repeating myself too much, and really to focus on the research that I've done at Madison, I'm just going to quickly go over some of this research that I did, and then we'll continue on with the newest stuff. So what I did at the Scripps Institution for Oceanography last summer was I found the evidence of an AR within this storm that we're talking about. And I did that through hand analyzing maps of integrated vapor transport and integrated water vapor. And then furthermore, I went and I compared it to more of a kind of traditional, stereotypical West Coast AR and found a bunch of similarities between the two, including deep saturation and low-level vapor flux. And we can take a look just really quickly at some imagery of that. So these were the initial images that I analyzed for both IVT on the left and IWV, integrated water vapor, on the right, to make sure that they were up to par, essentially, with the standards for an AR. And I was working in Marty Ralph's lab. He's pretty much the guy who defined these standards, so I wasn't really allowed to get away with anything. So this is a traditional defined AR, and then I took cross sections through these maps. We can see the CD transect across AR, so looking down the middle of it. Here we can see that low-level vapor flux, which is shaded in the rainbow color, sits at these really low levels, and that's associated with those higher winds, which are in the white, which is a pretty traditional kind of AR structure. And then if we look along the AR, so if we're looking at it going from our left to our right here, we can see again that low-level water vapor that's coming in with those higher winds. And this work was not done with reanalysis data in order to get these cross sections, but this was done with radiosonde data, so actual observations. So there was a lot of interpolation that had to happen, and like the Gulf of Mexico stations, this isn't going over the water, it's going along the coast of Texas. So a lot of interpolation here, but this was done with real raw data. And what I want you to take away is that I did find an AR structure within the storm. But let's move on. What I want to talk about first is how the snow got forced in that northwest quadrant of the storm. And so I tried to point this out as best I could in my synoptic discussion, but the center of the cyclone is really forced by divergence at 300 millibars, but that doesn't overlay quite as well with the snow band that fell. And so that is not I don't think, the driving synoptic force behind the snow band, but what I did find is that instead it is positive vorticity advection by the thermal wind that overlays that really, really well. And so here in these 4 plots, we have those same 4 time steps at 500 millibars. Our 500 millibar heights in black. We have our positive geostrophic vorticity in the red shaded colors, and then the green is thickness lines. And so what we can see in these diagrams, I'll point out to the B example, that along that really strong gradient of positive vorticity to the north and west of the cyclone center, it's going to track along these thickness lines beautifully, which just correlates fantastic with where that snow band fell. And again, in C, this is really that driving force. As we follow this vorticity gradient up along those thickness lines, it just cuts across central Wisconsin, right where that heavy snow band fell. So this is what I think is a main driver as far as the synoptic forcing goes for this snow band. And then further from that, what we can do for a lot of these occluded quadrants, what has been done, is really looking at the occluded frontal structure of the system and how that aligns with the trough of warm air aloft, which will give us a really nice outline as for where all of this forcing is lying. So let's talk about the trowel, or the trough of warm air aloft. This is a 3D structure where the cold air overruns the warm front, and we get this kind of upward cyclonically curving funnel, essentially, or trowel, of tropical warm air that is lifted and then allows for precipitation to the north and west of the storm. And this, you thought you were all going to get away without a little math, can be understood through QS convergence. And so when we have this kind of linear potential temperature feature, we have our delta theta vector, which is pointing uniformly at first, but with this QS convergence, that is not going to change the gradient of the theta vector at all, but what it will do is change the direction of it. And that, in turn, at some time step later, will lead to this thermal ridge in the theta gradient, which we saw in our Theta E environment during the synoptic discussion. And that's what really kind of transforms into this trowel or funnel feature. And so we can go beyond the theory and we can find that in storm. So if we look at our Theta E, so up in the top right, you can kind of see we saw this image already in our discussion with this kind of characteristic cyclonically curving back notch in the Theta E environment. And if we take a cross section through that, we see this beautiful picture that's in front of us. And so in the green is Theta E, and then the purple is upward vertical motion. And we can see that there's this very stark contrast with some of these Theta E gradients being brought down in this trowel region where that notch exists. And that's exactly where we find that really strong upward vertical motion. And so we can really beautifully conclude from this that yes, this is where our trowel feature is, and this is where we're seeing a lot of that forcing that's leading to upward vertical motion. And further from that, we've just looked at this in 2D, we can see that this 312K isentrope kind of envelops a lot of that vertical motion really, really well. So if we take that surface and we transform it into an isosurface, we can look at it in 3 dimensions, which is excellent because we can more fully see this beautiful 3D upward sloping trowel feature, which is exactly what our idea of this kind of occluded frontal structure looks like. And what this is going to do is denote an area around which the forcing of the occluded quadrant is organized up along this red line here that curves around. And this is from that same time for this storm. Just to give you guys a better idea of, or just to make sure that the structure of this is really organized, what you're going to see in this movie that's coming up is, again, that 312K isosurface, which is contoured by pressure. So those warmer colors are higher pressures, just to give you an idea of where in the atmosphere you are. And then the red that will be outlined is a different isosurface, excuse me, of 12 millimeters per second of upward vertical motion. So I will play for this and pray to God it's working. So what we can see as I kind of rotate this around in the image is that we have this trowel feature, and within that is pretty much perfectly aligned this upward vertical motion that flows Trowel picture beautifully. So that's where we're going to be looking, and that's where we can see our synoptic forcing lines up, but it's also where some more mesoscale forcings line up, because there is areas of more strongly banded snowfall further within the linear band that we see. So the first thing that I looked at was frontogenesis, as we go down and scale a little bit. This is 700 millibar frontogenesis for 0Z on the 24th, outlined in red with the mean sea level pressure in purple. And I'm sorry about the quality of this photo if it's not coming out for you guys, but we can see that along northeastern Texas and further up, there's the briefly outlined frontogenesis that is, of course, attached to the cold frontal structure, but that's not what I'm interested in. What I'm interested in is what's happening along the Minnesota-Iowa border, where we have this further pretty strong frontogenesis that's occurring in this short little linear band here. And so what's really kind of fun, I guess, about frontogenesis is that's in addition to that QS convergence. So those are two different forcings that are acting together on top of each other to really contribute to the precipitation forcing in this system. So if you take a cross section through that AB that I showed, the first thing that you're going to see here on the left is that frontogenesis, once again in red, vertical motion in purple, and then our Theta E, just to make sure we still have that Trowel feature going on, in green. And we do see it is there as we have this pretty substantial vertical dip in our Theta E lines, and that is again where our strong vertical motion is, and that lies really well, and I think is aided in part by this frontogenesis, which we can see, of course, at 700 millibars, obviously, but also strongly down at the surface, and not just in that particular location. But is that really the whole story? So I dug a little deeper to see if there were any further instabilities that we were looking at to really contribute to heavy banded mesoscale snowfall within this system. And so this other cross section I'm presenting to you is, once again, same Theta E lines in green, and then that kind of pink magenta color is absolute momentum, M, and then the red coloring is negative equivalent potential vorticity. So what this is going to tell me is where there might be potential instability or conditional symmetric instability. And so we can see that for a large part of this, the Theta E gradients, or the Theta E line slopes, are less than that of the M slopes. And so that's where we have this pretty strong area of potential instability. But there are some areas within this cross section where our M slope is less than our Theta E slope. And so we also do some areas of conditional symmetric instability. It's worth noting that those are things that you can diagnose in a linear feature of frontogenesis, and I'm making the claim that this small area of frontogenesis that I took this cross section through is fairly linear, but it's worth taking with a grain of salt that it could be exhibiting some curvature. So, and furthermore, if we just want to check ourselves with that, at that same time period, I'll go back for a second, we can see that this area of forcing is, or forcing rather, is really over this Minnesota-Iowa border area. And if we check our radar reflectivities at this time, we can see this beautiful, strong area of snowfall. And it was recorded as being snow at this time. So that really kind of a nice overlay of both our synoptic forcings, producing a broad area of lift, and then further enhanced by some of those mesoscale forcings. But we can have all of the lifting that we want, and it won't do anything if there isn't any water involved in it. And so that's kind of what I guess I thought was the next obvious question to ask is, where is the moisture coming from? And we've kind of ID'd that this atmospheric river is feeding moisture into the storm, but how does it get from those southerly locations where the AR is up into this snow band, which we know is being forced? And it is worth noting that this is obviously not the only time that water is being processed within this extratropical cyclone. Some 30, 35 hours earlier, we can see that the snow is not well developed at this time, but that really heavy rain band over the southeast is. So there were a lot of different parts of the storm that needed to be processed and needed water vapor in order to occur. So the last part of my research that we're going to dive into is these moisture trajectories in order to analyze what pathway moist parcels took in order to get to the snowfall. So I'm going to step through just 3 different time steps with you guys on these and really try to make sure that you understand the 3D structure of what's happening, because this, I think, is the most fascinating part of this entire research that I've done. We're going to start at 18Z on February 23rd. This was a time when snowfall was occurring kind of over the Oklahoma, northern Oklahoma area. And every single picture is going to be very similar. It will be these trajectories, and they will be contoured by mixing ratio. So the warmer colors is a higher mixing ratio, cooler colors the opposite, and I'm kind of taking that as a proxy for how much moisture is within this parcel. And so we can see for the trajectories that are ending at 18Z, and these are all initialized within that Trowel region where the vertical motion was, we have this pretty direct path from the Gulf of Mexico all the way up to this northwest area of the cyclone center. And if we take kind of a 3D view of it, looking from the southwest over from the tropics of the Pacific, we can see that these trajectories start out at a really low level and then pretty rapidly increase. And these are a little funky because they didn't quite have the resolution I wanted, but we're going to improve that at the next time step. But overall, what we can take from so far is that we have really high moisture parcels coming off the Gulf of Mexico and then rising rapidly as they are intersected through the Trowel and the forcings that exist there. Let's step forward 6 hours. Here at this time, we can once again see that we have that path from the Gulf of Mexico into the snow band. And 0Z on the 24th, that's when we just saw that we have some pretty heavy snowfall going on over northern Iowa into southern Minnesota. But these don't seem quite as straight as the other ones. So if we take a little bit of a 3D view, once again, from that kind of southwest perception, what we can see here is that these trajectories are once again coming off the Gulf of Mexico at very high moisture contents, very high mixing ratios, and then a large chunk of them, a good percentage of them, are being involved in some kind of ascent and descent pattern over the southeast. About 25 to 35 hours earlier than when they are involved in the snow band. They go through this period of ascent and descent and continue on to further be involved in the snowfall. And what is further fascinating to me is that these trajectories, and you'll have to kind of look close / trust me that I investigated what their values were as far as moisture content goes, they lose a lot of their mixing ratio in this initial ascent. We can see those colors going from warm to much, much cooler colors, almost to blue, into those teals, and they reach their kind of peak dark color at the very top, and then some of them are actually a good chunk of them actually then on their way down poleward of this feature increase just slightly their moisture content or their mixing ratio. So that's really fascinating, to the point where if we look at our top level, that a lot of these trajectories come down after this period of ascent and descent, this kind of roller coaster ride that they've been on, to the point where they're at about the same mixing ratio level before they are involved into the processing into the snow band. One more time step, because this is just one time period, right? This could be a fluke, it could be a weird thing with the data. So let's hop ahead 6 hours. Once again, this is when the 60 on February 24th, this is when we're seeing heavy snowfall over much of the Wisconsin area. And we can see again this Gulf to snow trajectory. And for these guys, it takes almost 54 hours for the parcels to come all the way from the Gulf of Mexico to the snow band. And we can see this notch on the top here again, where that ascent and descent pattern might be found over the southeast. And this time I'm not going to give you the 3D kind of view, but instead we're going to look at a kind of cross-section area from the east, so south to north, left to right. And we can see, once again, those high moisture content parcels coming off at a very low level near the surface, near the Gulf of Mexico. They rise rapidly in this ascent and descent forcing over the southeast, descend possibly faster, and then progress onward to be involved with the snowband, which is really where they lose a lot of their moisture. It pretty much goes to zero as far as the mixing ratio is concerned. And my hypothesis is that these parcels are being involved in convective processes over the rain band in the southeast. To give you guys just a final 3D view of these pathways, I have two little movies involved. This first one is going to play through the trajectories on their course. I'll play it a couple times. So we can see them coming up from the Gulf of Mexico, doing this little roller coaster loop, and then falling down near the surface before they rise very rapidly and lose a lot of their moisture over that Trowel region. And then just to kind of give you guys the full view, full 3D view, I'm going to rotate this pathway around a little bit more, just so everybody can really see that strong moisture near the surface coming in from that feeder air, from that AR, getting involved, being pulled through the system into the warm conveyor belt, involved in convection in the warm sector, descending on the poleward side of that, and then furthermore going and being involved in the snow. So this really kind of beautiful recycling almost of water through the system. So let's wrap it all up. I think we've had a bunch of bits and pieces of the system here. And so what I've found in my research is that these continental cyclones, or at least this one, it is worth noting that the one case study can be found to have this AR, atmospheric river structure, which is going to act as that feeder airstream into the cyclone, delivering high moisture content into the storm. That is further carried away, and we can find that we have these really prominent synoptic and mesoscale forcings that are contributing to a heavy linear snowband in the occluded quadrant. At a synoptic scale, we found that positive vorticity advection by the thermal wind is really largely driving where that snowband is occurring to the north and west to the cyclone center. And then furthermore, we identified areas of frontogenesis, potential instability, and conditional symmetric instability that add on to accumulate snow in these fine, more mesoscale type features. And that can all be largely organized or seen to be organized through this trowel feature or this kind of diagonal structure of the warm conveyor belt, which curves cyclonically around the cyclone center. It's the same thing. You have this warm tropical moist air that's being forced up and around into the occluded quadrant. And then a really fascinating part of this are these moisture transport pathways that are able to deliver moisture to multiple forcing mechanisms, which I think is absolutely fascinating because these trajectories, they follow the trowel into the occluded quadrant after having been essentially recycled in the southwest part of the storm, where you have cold frontal convection or something happening in the warm sector. And we really see this repurposing of the available moisture, which I think contradicts our kind of traditional thinking, where this would typically be termed a kind of robber storm, and the convection to the south would rob the snowfall of available moisture. But instead, we see this repurposing happening. And there is extremely limited literature on this subject matter. But what I did find was a master's thesis from the University of Milwaukee. And this master's student did a comprehensive view of a lot of these different robber storms and found, similar to what I'm finding, that there is this recycling and repurposing of water, and that it does lead to observed lower snowfall amounts, but because it is actually leading to lower snow to liquid water equivalent ratios. So that's in essence leading to a smaller snowfall observation, but it's because it's heavier, denser snow. But there's a lot of research that could definitely be done about that. And then overall, this entire picture that we're seeing of this feeding of moisture into the system, the pathway of the trajectories as they take through the storm, and then being involved in these synoptic and mesoscale forcings in the occluded quadrant to produce snow it is supported by a lot of research that has been published in the last 2 decades about extratropical cyclones and how their major flows work. And what I think, or what I'm particularly proud of with my research, is that I think it pieces together a lot of those bits and pieces that we've found about extratropical cyclones to kind of make this full story of the moisture and how it gets to those beautiful snowflakes that we get to see in the winter. With that, just some quick ideas about future work, because it never ends, is something that we did want to do with this storm but couldn't possibly have the time for due to our current situation, is doing some modeling with the WRF to investigate even further this relationship of the convection and snow. We are limited in the research that I did. I was limited by the 6-hourly resolution of the GFS and a more coarser resolution. So we really wanted to dive into that a little bit more. And so that would be an excellent path of future work to take. And then I have kind of made a little dream for myself in terms of a field project that could go on with these extratropical cyclones, which is using hydrology to identify water sources throughout these snow bands. So taking samples of that snow and through the water's isotopic signature being to trace it back to the source, I think would be an absolutely fantastic hands-on application of this work. With that, I have a million people to thank for all of this. The team at the Center for Western Water and Weather saw the very beginning of this research, and they kind of let me take my own path last summer, and to them I'm eternally grateful for letting me do that, and as well as getting experience in the field. Professor Martin has heard every single dumb idea I've had since September and has most patiently guided me through research and given me a million ideas and several different proofreads of my paper at this point. And so thank you so much to his advising. Pete, I would be lost without you. This department would be lost without you. So thank you so much for doing what you do and promptly answering your emails, whether it's noon on a Wednesday or 5 p.m. on a Sunday. You've been there for all of us. So thank you so much for your constant dedication to this department. As well to every single professor that I've had in the last 2 years. If you're watching this, I really hope that there was some part of this process that you saw and said, hey, I taught her that, 2 years ago, because I really feel like this research is a beautiful culmination of everything I've learned in this department, and I couldn't have learned it without the help of my fellow students. The graduating class of 2020 is an amazing one, and I couldn't have learned it this well without them. And to every single family member that I have, whether it's my chosen family or my given to me family, Mom, Dad, I hope that even though you maybe didn't understand a lot of what was going on in this presentation, you saw that putting me through college was worth it, and that I really learned something and got something out of it. And to my chosen families at both AOS and on the Nordic team, thank you for always being there for me, and my ever supporting partner, Jess. Thank you. And with that, thank you all for listening and being here at 8:30 a.m. on a morning. And I will leave you with this vista of a tipping bucket in California and ask if there are any questions. Thank you.
Thank you very much, Ketzel. Excellent presentation, and we're happy to take questions. Ketzel worked hard to make sure that she came in. What is it, Ketzel? It's right at 40 minutes or something like that, and 35. So we're right on time for a broad array of questions, if there are any.
Hi, John. Can I start? It's Elizabeth here.
You sure can, Liz. Thanks.
Ketzel, that was fantastic. I'm really impressed. That was awesome. I think my question is a bit broader, though. I'm curious, what's next for both this project? Are you planning to write it up? And what's next for you? And then I've got more of a story. So this is something I'm curious to get your thoughts on it. When I was a first-year grad student, I went to a master's defense. It was on atmospheric rivers. And the question period, the faculty got into this heated discussion about this existential nature of what is an atmospheric river. How much is it tied to that cold front? Is it really a separate beast? And I'm curious if in your time at Scripps and your time doing this work, if you've had any thoughts on what is really an atmospheric river.
Those are two fantastic questions. I'll start with the first about myself, I guess, which is, as far as this work goes, I don't know if I would necessarily continue it. I enjoyed it deeply, but would like to move on to other things. I'm interested in exploring other aspects, specifically, that field project is really from my desire to work more deeply in hydrometeorology and understanding those connections, possibly more at a meso or micro scale. At this point, I am taking at least a gap year with my partner. We're moving to Duluth tomorrow, actually. I'm standing here in my partially packed apartment. And so I'm going to take a gap year, and then I'm probably planning to come back to grad school to further my education in atmospheric science. And then if somebody else wanted to take on this work, I would gladly support them. I think it's really cool and interesting. And as far as the atmospheric river question is concerned, this is something I've had a lot of discussions about with people, and I got some pushback, I guess, in my initial presentation that I gave last October. And if I might let me just flip back real quick, because I think there's a visual that can kind of help me with that. The understanding that I have come to, and this is why I really like this image from the Martinez-Alvarado paper from 2014, is that the atmospheric river is a connection that these extratropical cyclones have to these tropical moisture sources. And there is certainly a transition where it goes from atmospheric river to warm conveyor belts and processes along the cold front. And where that exactly is, I don't think I have the authority to say, but I like to view it more as just the kind of delivery person of moisture into these systems, and then there are processes within the extratropical cyclone that takes over. But I think it is important to understand that they are their own phenomena. I think that they are their own phenomena, and that it's not just something from the tropics that's pushing upwards, which is what Professor Tripoli might argue more, or if it's the extratropics that's just pulling something up into it, that there is this significant kind of bridge that they make between the two systems.
I have a quick question and a comment. First, Ketzel, that was a wonderful talk, well organized and really informative. I learned a lot about this, and I appreciate this. That one of the points that you made about this sort of repurposing or this recycling of water as you go through a convective system. And I imagine it's in this when the air partial is descending, it acquires some of the water vapor that's being evaporated from rain falling above it, and that's what remoisturizes it or re-energizes it in terms of water vapor content. Yeah. Elizabeth's question about what is this atmospheric river, I think another perspective or additional perspective in this is the notion, figure that you have up there, is that if you view these rivers in a frame of reference moving with the weather system itself, this would be with any weather system, but in particular one that has a nice extent cold front, you'll see that these occur in regions where there is a confluence of airstreams. Anytime you see these banded structures, it perhaps has something to do with deformation in the flow, but maybe not in a frame of reference with respect to the Earth, a frame of reference moving with respect to the weather system. That's, I think, how Carlson, back in, I don't know, the years, in the 70s or early 80s, defined these warm conveyor belt structures. Maybe it goes even before Carlson, but folks in the UK define these airstreams. But it's in this region where you have deformation occurring. And so I'm wondering, have you done any analyses that look at these systems in a frame of reference moving? You come up with an estimated translation speed of the system as a vector, and then subtract that off the full winds to see how well the atmospheric river lines up with regions of confluence in this different frame of reference. If this question makes any sense at all. But I just want to end the whole presentation.
Thank you. Thank you very much. Yeah, the question makes sense, first and foremost, and it's an absolutely fascinating way to think about this, and it's not something that I've done. When you look at these systems, and I'm kind of now kicking myself for not including a GIF of water vapor going with the storm, but like you said, these atmospheric rivers do seem to move really closely in a line with the speed of the storm, and it would be yeah, it would be really interesting to see how those line up, and just in like, you know, the plots of winds that I've looked at. I haven't done any formal analysis of what you're talking about. And it really is. It's an area of pretty observable confluence in these regions. So yeah, that would be a fascinating thing to take a look at.
Right. And I think your work points to a sort of an immediate thing. Some people have this concept of the atmospheric river as this continuous stream of water vapor transport, but there has to be this reprocessing. I think what your work is kind of suggesting that there's going to air and water vapor is going to precipitate out, and then some of it's going to re-evaporate to continue the stream as it moves northward to higher latitudes. And I think it's just fascinating what you saw with some of the trajectory analyses. But thanks for a great presentation.
Yeah, thank you. And yeah, what you said is when I did these trajectories, I guess I should have expected to see some influence of the convection in the southeast, and it took me by complete surprise. I ran these VIS 5D trajectories, and I was like, oh, wow, this is absolutely fascinating. And what you said about that kind of evaporative effect, increasing the moisture on the poleward side is exactly what my hypothesis is about how we're actually seeing some increases as well in that vapor moisture that continues on into the snowband. Yep.
Yeah, I think this recycling of water substance is a very interesting aspect of it. And Liz's question that Michael amplified in a different direction is really fundamental here. I think it's really true to, if one were to continue pursuing work like this, I think you'd get farther and farther afield from really relying on the atmospheric river as the key, docking point for your argument, because you'd end up probably believing that the river is just a function of larger synoptic and even mesoscale dynamics, which I think your work's pointing out. And if you don't understand how those dynamics are processing the water vapor that's delivered, as you said, Ketzel, by this feature, then you don't really know how the storm is working. And so one could make the mistake of coming to an understanding of how the U.S. Postal Service works by watching one mail person every day. And that would be a mistake. You don't know how it works by looking at one element. You have to understand the complex system in a way that goes well beyond the one little element of it. So, but I think this idea of the water recycling, I think if I'm right, Ketzel, those trajectories were made from 6-hourly GFS analyses. Is that right?
That is correct, yeah. So they are pretty...
So our desire to go to the higher resolution real simulation at half-hourly time steps would have been really interesting, and that could be something someone could do, because you could actually trace those trajectories and see just how much water substance is actually being reprocessed in the downdrafts when it's evaporating or sublimating back to water vapor. I think that's fascinating.
Exactly. Yeah, this is in terms of, I guess, the modeling power that we have at a pretty coarse time scale. So I can broadly say that this entire kind of convective ascent descent feature takes roughly 12 hours, but I think there's a lot of small subtleties that are probably being missed in this data set. And yeah, I fully agree. The atmospheric river, in my mind, is just one piece of the puzzle. It's like doing a puzzle where you just put the outer pieces together and you're like, I've done it, I've solved it. I think it makes for a really important part of the overall moisture structure of these storms, but it can't be the whole answer.
And if you're living in a location where the topography has a tremendous profile, then it's a big enough part of the answer that you don't have to say any more. If you've got a river of water vapor crashing into a steep slope, that's why it's raining where you live. You don't rely on synoptic and mesoscale dynamics beyond the organization of the river. You're just letting it smash into the wall, but not true everywhere else.
Exactly, yeah, and that's what was really fun about doing some of this work in San Diego is my colleagues there at Scripps, they're really used to seeing this integrated vapor transport, integrated water vapor just slamming into the coast and then kind of disappearing, because they rely pretty much on orographic forcing for all of their precipitation. But obviously, the Mississippi Valley doesn't have any in it, so we have to force our precipitation in different ways, and that really changes the story when we look at these more continental storms, I think, which is why I found some of this very fascinating. And I can't see the chat. If there's questions there, if you could read them off to me. But
yeah, Carrie had a question. I'll read it to you. Carrie's question was, how high does the recycling have to be in order to produce the moisture needed for the storm? And by how much does the intensity of one storm to the other, she wonders, will that change the amount of moisture recycling? Good questions.
Yeah, fantastic questions. I'll kind of move into this one. As far as how high, if I'm understanding your question, that's a question I didn't ask in this, and is really fascinating because obviously this convection is going to take off and could even reach tropopause level if it really wanted to. It doesn't appear to be doing that here. But I would assume that it needs to reach some kind of height in order for it to lose a lot of its moisture and then have the amount of descent to really gain some of it back. But we can see that once it reaches the occluded quadrant area, it goes shooting off to the tropopause, and it's pretty much gone. And I don't have a height scale on here, so I apologize for that. And then I mentioned in my conclusion that this is just one storm, and every single storm is going to be unique in what kind of rain structure it has versus what kind of snow fall it will observe for it, and so that is the part of my future work slide that I forgot to include, which is going through and doing more of a comprehensive analysis of more cyclones like this one to see what kind of similarities and differences there are in this repurposing of water, because I would imagine that it's going to depend a lot on the timing of the snow and the timing of the rain in conjunction with each other, and then how, what time of year it is going to determine how strong that convection in the southeast might be. So there could be this kind of sweet spot in terms of when these storms are hitting, where the convection and rainfall that's occurring in the southeast isn't too severe that it's really using a lot of moisture in its systems, and it's able to move forward. And maybe those robber storms do exist, that there are storms where the rain in the southeast is so much that the moisture can never make it far enough north, or the parcels end up far enough north that they just kind of are dry, and Professor Martin and I are really, really sad. So there's a lot of work that has to be done with more of a comprehensive analysis of a multitude of storms with this, because those are absolutely fascinating directions that could be taken. Anything else?
I had a question. This is Maria, about generally about where you see atmospheric rivers occur. I guess a lot of the research I've seen in the last few years about atmospheric rivers have focused on the west coast of the U.S. And I just wonder how often these occur, from the Gulf of Mexico up through the U.S. that way. Is it more rare that you have atmospheric rivers there, or is it just, I just haven't happened to see much research on that?
Yeah, it is, and that's something I kind of had to search for when I was starting this project out, because we have these more stereotypical, well-documented ARs that happen on the West Coast and in the Pacific, because they are very impressive, and over that kind of ocean environment, it's really easy to pick them out, because it's oh yeah, here's this really strong band of moisture that's being transported from the tropics. And so I think it's probably also for an ease of studying them that they're really well documented there, and they make up a huge chunk of California's water budget. So they're really important in terms of that as well. There is some research that has to do with this kind of Mayan Express. So the one on the West Coast is known as the Pineapple Express because it comes from Hawaii. So this is more of that kind of Mayan Express that comes, or appears to come, from that more central Mexico area, with moisture coming out of the Caribbean and the Gulf of Mexico. I don't know if it's a function of there's just less of them, if there aren't as many cases that are recorded, or if it's a function of we don't identify them as atmospheric rivers when they do occur in this area, and then they're just not counted. So it's a really kind of interesting question in identifying this system as having an AR, because we don't usually say, oh yeah, this is this atmospheric river that is connected to this mid-latitude cyclone, like we do in the Pacific, when it could be that it certainly is, and we're just not counting them. They also are really well known to hit like Western Europe and Scandinavia in the mid-latitude cyclones that progress across the Atlantic. So they're well documented there as well, which is, again, you know, one of those environments where it's more of a open ocean versus dealing with a lot of these continental processes.
Yeah, the other common denominator there is that both these regions are at the end of the respective ocean basin storm tracks.
Yes.
With some variability. And so, you know, the Gulf of Mexico is in between the climatological jets. The Pacific jets, when it's extended, it crashing onto the west coast of North America. The Atlantic jets pointed from, you know, Georgia to the British Isles on average. And so in the Gulf of Mexico, there's no jet at all, except the subtropical jet, which is highly variable and too high to really drag the low-level water vapor in. So it relies on the invasion of troughs from the northwest.
Right. I wonder if another aspect of it is, as you said, John, they're near the end of the storm tracks. Since you've had a cyclone developing across a large ocean basin, whether it's the Pacific or the Atlantic, it has time to organize the kinematic fields to produce the confluence or whatever is necessary to generate these concentrated areas of transport.
Yeah.
And something moving right off the Rocky Mountains, depending on its initial intensity, goes back to maybe Carrie's point. The intensity and structure of it hasn't come together yet to fully give you these concentrated regions. And so it might be, I wonder if there's a variability in the identification of these based on the stage of the life cycle of the cyclone, how rapidly the cyclone develops. Maybe you might be more likely to see things defined as ARs in a more rapidly intensifying cyclone than something that kind of meanders across the continent before really developing, you know, coming together.
Yeah, that's an excellent point. And I think Ketzel's along river cross section really shows that the fetch had to be perfect across the Gulf of Mexico to actually adopt the characteristics that Marty's kind of outlined for these atmospheric rivers in an environment, as you point out, Michael, that's had many, many more hours, in fact, days to shape the length, the aspect ratio of these things. It's so much harder to do that if you have a straight southerly flow off the Gulf of Mexico, off the Yucatan Peninsula. How are you ever going to get something 1,500 kilometers long in a day? You're not going to do that. So, but if you go all the way from, you know, the Bay of Campeche to, Pensacola, that's the long fetch, and that's about what it was in Ketzel's storm. So it's kind of an interesting point.
Yeah, and I have two comments in response to that, which is this storm did occur in this kind of not stagnant but continuing pattern that I was seeing in the integrated vapor, where it was continuing. It had this kind of beautiful clockwise curvature to it, where the vapor would come up from the Caribbean, go through smack in the middle of Gulf of Mexico, and then curve out and kind of meet the Atlantic Ocean in the central eastern seaboard. And that pattern continued for a while and made kind of these several rounds of these storms that impacted the southeast and us as well with snow. And then my second comment is something that Dan Weimont actually brought up in my October presentation that I really wanted to do with this research and didn't get around to, was investigating more of an Alberta Clipper type system and seeing where that moisture is coming from and how it's processed into that snow band, because it's a much different system than this kind of Colorado low event that I looked at here.
Yeah, in the first order of business in a study like that would be, what's the total liquid equivalent precipitation delivered by either type storm? And I think the Clippers will be 1/5 at most of what you get from one of these things. And so, you know, you can get snowfall totals that are substantial and certainly hazardous conditions, but the water content is really low. It's just that the air is so cold that it can create some 30-to-1, 40-to-1 ratios.
Yeah, exactly.
Any other questions for Ketzel? Well, if not, thank you everyone for coming and for some great questions. Liz led it off with a great question. I think we never really let that question go. We were talking about it all the way through, and I think it's a very important one. Sometimes it's easy to get focused on features and the names people give them, and then you start to forget that they're not mythical creatures, or maybe they are mythical creatures, and you have to think about what's actually underlying them instead of them themselves. And I think part of our conversation today was definitely dedicated to that. So Ketzel, thank you again for a great presentation. Congratulations on your exciting work, and travel safely up to Duluth, where you'll enjoy 1 week of summer sometime in mid-July. So I hope that it's as warm as you expect it. So,
I can't wait.
yeah, that's great.
Cool.
Okay.
Thank you, everyone.
Yeah, thank you again, Ketzel. We'll be back next week. I think Zoe's going to present for the week that she had to miss for illness. So we'll check on that. And if that's not the case, I'll let everybody know.
Okay. Thanks, Ketzel.
Thank you.